Okay. Am I audible? Am I audible? Hello. Hello. Anybody there? Hello. 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 Yeah. I hope I'm audible. So today is our last session for this semester, and yeah, and this will be our live session 12. So today, what we will do, we will mostly spend our time on this welding defects, different kinds of welding defects like uh, surface and subsurface welding defects, different issues we observe in welding, and how do you design for different kinds of loading, uh, and then what about this fatigue loading in welding. So those things we will try to brush up again, whatever you have gone through your video lectures, right? So so in terms of defects, basically we'll have the discussion on welding defects, and we'll try to have the knowledge about these defects which arise because of lot of reasons, right? So there are a lot of reasons for which welding defects occur in general. Now, what are different defect types, and so we'll certainly discuss whenever we'll spend our time in our this this video lecture. Now, so what is welding defect basically? So this is the performance of your weld structure, uh, which depends on your quality of fabrication, right? And uh, there can be presence or absence of defect in the weld joint, of course, and any kind of deviation, if it is there from the specified requirement, that basically tells you that you have the defect in your particular component, right? So as I was saying, your performance of your weld structure depends on quality of fabrication, right? And then your defects basically uh, impair the strength, and then you'll have some failure will happen because of if there is presence of defects, right? So uh, now the principal causes which are the reason for this failure, uh, which are the reasons for this failure to follow the requirement of welding specifications. So what are the reasons? So, like, the main reason which is there for this welding defects are that you are not able to follow the requirements of welding specification. That is what I was mentioning. So and then many a times it happened that we use some substandard materials. So then also we can have some defective welding equipment. uh, that also many a times can be a reason for defect formation. And then sometimes you have some poor welding skill also. So for welding skill is a concern, right? So whoever the welding operator is, he should be highly trained and skillful in doing the welding, right? So the manpower which is there, that that should have the adequate workmanship, right? And then so there can be some design or drawing errors also, right? So there can be design or drawing errors also in terms of getting some defects in your welding. And that also can be a reason, because the joint design or the gap or all that which you are trying to give, that may not be proper one. So it all depends on your how you are designing your structure, right? So as your design may not be proper, that may also lead to the generation of defects. So that way you have the chance of having those defects. Now in terms of classification of welding defects, so in terms of, if we try to classify what are there for welding defects, so you can have some crack formation, right? Then you can have some cavity formation. Then you can have something called solid inclusions, right? And there can be some kind of incomplete fusion or penetration. And then there can be some imperfect shape also. Those things are there, right? So these cracks are different types of cracks. Like you have cold cracks, you have hot cracks. So those things we have discussed in our earlier lecture videos. So as I was saying, there can have cold crack, then hot crack, then you can have some crater crack, uh, something called toe crack. So on the track you have lot of we have the understanding in our earlier lectures, right? So then you have cavities. So cavities are also very important type of welding defect, because we have understood that when we are doing the welding, during the process, cavity mainly occurs because of high temperature. And if there is no proper shielding, and if there is no proper shielding from the environment, if you are you're not having proper shielding, then what will happen? So in that case, there may be some gaseous pickup, or there will be some dissolution of the gases in the well, right? And many a times some of the gases has very high solubility at very high temperature, and very low when the temperature drops. So there will be gas solubility will increase.
Sir,
Huh.
cavities and porosities are same or different?
um, kind of. So if you are thinking of porosity, it's smaller in nature. It's smaller in nature. and depending on shape also, how it is looking like, depending on that also, some abbreviations are there. Cavity is mostly big enough. Then you call sometime you call it void also. No, so the physics is a similar kind of thing. Because of this entrapment of gases, or there can be this hydrogen entrapment in the liquid melt pool, and like, if your solidification time is very, what should I say, if your solidification time is very fast, uh, then your this gas entrapment, like, they cannot get enough time uh, to escape from there, right? So uh, the porous structure will form from there. Now in those cases you can have some, so there is something called blowholes also. There is something called blowholes also. So you can have blowholes in the case of welding, where the holes are there inside the weld pool. So holes are inside the weld pool. I'm just giving some brief characterization. I'm not going into depth in for this first question. So here the blowholes are inside the weld pool, and then you have the chance of having porosities, right? So you may have some kind of shrinkage, and those different kind of cavities which are getting generated, that may happen because of shrinkage also. So there is something called shrinkage cavity because of difference in coefficient of thermal expansion, right? So yeah, many a times you can have some metal oxides also, and when you use some tungsten electrode, so in those cases you have those entrapment of those tungsten also, right? So that also may go, and that may seen in those cases. So they are basically coming under these solid inclusions, uh, and then you have this incomplete fusion or penetration. So we have seen that there can be this lack of fusion and lack of penetration, and uh, you are not able to penetrate properly, and then you have the suck back effect, something called suck back effect. So that yeah, that phenomena may also be there. And then you are having some imperfect shape. So imperfect shape means that uh, the contour which you are getting, that is unacceptable, right? So the way it looks, that is basically not acceptable, and you have some dimensional deviation from the actual one, right? And you can have some undercut, or you may have some underfill, and then there are also chances of overlap also. So these are different kinds of defects which are structurally you can see when you are doing some welding, right? And many a times what we do is we give the excessive reinforcement also, so that that may also come into that category. Then excessive penetration is there, or the uh, bead shape which is not proper, that is also there. So all these things under the category of imperfect shape, or maybe some unacceptable contours, those are there, right? Now what else? So you can have some arc striking, right? In terms of defects, you can have uh, arc striking. So what will happen during the earth striking? So you can have the excessive spatter, right? When earth striking is there, excessive spatter can form. And then you have some, because of those excessive spattering, because of those excessive spattering, you can have a rough surface generation, right? So because of excessive spattering, you can have rough surface generation. And that is another kind of defect which is likely to come in the case of welding. And you can have some uneven ripples and something called pock mark. So you can have some uneven ripples and pock mark over your welding structure, right? And these defects which are coming, that can come under some miscellaneous kind of defects, right? So whatever I am talking additionally from these things, that can come under miscellaneous defects, right? It's not obvious that every time you are getting these kinds of defects, there are a lot of other defects also which you can get during your experimental observations. So yeah, so what we can do is welding defect is basically, you can classify it in different ways also. Like there can be something called visual or surface defect. So this is another kind of classification where you can have this visual or surface defects. And in another category, you can have these hidden defects, right? You can have hidden defects. Now, in the case where the defects which you are able to see, those are visual, or so those are visual. That kind of defects are called visual or surface defects. And where you cannot see them and they're inside or below the surface, that is called hidden defect, right? So if you try to have the example of these visual or subsurface defects, so in that category we'll have these surface cracks, right? Now then we have something called distortion also. Distortion or wrappage which is created because of this surface crack. That means the crack which is exposed to the surface on which it is appearing, right? And is happening? So distortion is generating because of the residual stress values, right? Or the restraint which you have studied earlier. So there basically you can see this, you can see visually that is under the visual crack. And then you can have some incorrect shape profile or bead profile, or bad incorrect bead profile, uh, whatever is happening. Now this profile which you are able to see, that may be incorrect, right? So that is, if any kind of overlap is there or undercutting is there, those things are incorrect in nature. So that we may discuss later on. And as I was saying, there can have this dimensional deviation. uh, those things are there. And then you have this underfill thing. And then you can have this excessive penetration. And apart from that, what you can have, apart from that, what you can have, some unfilled craters maybe. mm. So these are coming under visual defect, right? So these are coming under visual defect. Now you have the surface porosity, right? You have some surface oxidation, and these are among these defects which are uh, visual or surface, like surface pattern is there many a times that can affect or creates the unevenness on the surface or surface finishes. So those also are those are also coming under this visual or surface defects. Now if you talk about hidden or subsurface defects, in those cases you have this what can we have in terms of hidden defects? So in terms of hidden defects, you can have this um, you can have this lack of fusion. So you cannot see visibly from outside, right? So lack of fusion or lack of penetration. So then you have this shrinkage. So for shrinkage cavity, again, you have to find it using some spatial means, that what where the shrinkage cavity is there. And then you can have something called slag inclusion, right? So these are coming under hidden or subsurface defects, right? And then you can have some coarse microstructure that also you cannot see in naked eye, right? So that is also a defect. And coarse microstructure will be uh, it can be one of the defect which is type of as I was saying, that can be hidden in nature, right? So coming to the question, coming to the question, which of them is not a kind of welding defect? Solid inclusion is a welding defect. Imperfect shape is a welding defect. Cavities is a welding defect. Are you familiar with uh, alligatoring? So this is not a welding defect really, but this is a defect which generally forms during metal forming. Right?
Yes, sir.
So alligatoring is defecting. So this is basically, if we try to define it, alligatoring. I'm not going into much depth of how does this form. So This is basically some splitting of a piece of sheet metal to form two open ends. So this is what is called alligator. Okay, okay. Now, now coming to this source of welding defects. This way. Yeah. So now coming to the source of welding defects, you can have various sources of welding defects also, right? Source of welding defects. So in terms of sources, what can we have? We can have improper selection of process, right? Then you can have improper application, right? Then then you can have this kind of interaction of the weld structure with prior defects, right? Then you can have some undesirable metallurgical structures in terms of microstructures, those coarse microstructure things, right? So undesirable, that's a microstructure. What else? Then you can have some incorrect age preparation also, right? Then you can have some poor design. So these are some of those sources of welding defects, right? Now, if we take if we take some improper selection of welding process, the end result may be not very rewarding. If you are taking a process which has very deep penetrating heat sources, and if you are putting on the very narrow V angle, right? So your heat source is very high, and your uh, so the V angle is very narrow. Are they compatible? So basically, it will cause the crack in the root because of very large depth to width ratio, right? So crack formation will be there because of large depth to width ratio. So in those cases, you will have to have the proper selection or proper selection of the welding process, and so that you get some desired results after the welding, right? Now, in terms of improper application of welding process, uh, what do I mean that in that case you are using some improper application like improper shielding gas, or uh, you are not choosing appropriate welding current which you need to select, or else depending on the dimension of plate or so huh so depending upon your dimension of the plates to be joined, or depending upon different processes, uh, you have to have used some proper current setting, right? So uh, yeah, excluding that there can be some gaseous shield is there that is not adequate, or maybe you have done some improper weld deposition. So those things are there in terms of improper application of the welding process, right? Now these things basically will be leading to this improper result of the defect formation in the weld specimen. And then in terms of interaction of weld metal with prior defects, what do I mean is that uh, many a times it happen that weld metal that will be interacting with the defects which is already there in your sheet metal or the base metal. So basically you will have this lamination, and you have the uh, impurities like phosphorus or sulfur. Those things are there, right? So once you'll have that interaction, that may result into this undesirable structure, or you can have some brittle zone formation, and that may result into this uh, what do we call that as lamellar tearing, right? So if you have, suppose you have the lamination, and you'll be interacting with these impurities which are there. uh, we have already studied this lamellar tearing, right? And their interaction may result into the kind of tearing which is observed usually in welding as a welding defect, right? Now in terms of grain size and hardness, you may have the undesirable microstructural or metallurgical structure that can be because of those inclusions, such as what I was talking about, this tungsten oxide or those slag inclusions are there, right? So these inclusions will also going to have the effect because they are undesirable microstructure, right? And similarly, hydrogen is another principal constituent material. Hydrogen also is a principal constituent material which is very much undesirable, and most of the time it happens that hydrogen is responsible for this cold cracking. Right? So you'll have to have some control on the presence of hydrogen inside the weld, and uh, we do that by doing some shielding, or so you should have some proper shielding, or you can do some welding in your argon gas environment. So those things are there to reduce the possibility of this hydrogen formation or hydrogen entrapment. And you can also have some bubble formation because of hydrogen, right? So argon environment. So yeah, lot of things are there. Hmm. What else? We have this age preparation, right? So so apart from this undesirable shape and the size of the weld bead, you can have this incorrect age preparation. So first of all, before that, you have this undesirable shape and size of the weld bead, right? So here again, you'll have to look into the weld profile which you are getting. So there may be many reasons. So you can have this overfill, you can have this overlap, then you can have this undercut. So these are the so under this category, you have this undesirable shape and size of the weld bill, and basically you want a particular uh, or ideal shape of a weld bill, right? So if there is more deviation. So the deviation may be in many forms, as I was saying, this overlap and undercut things. And yeah, and then you can have this 4 feet up also. You can have this 4 feet up also. I'm trying to figure out lot of terms here. So you can have this 4 feet up also. That is also there, right? So in those cases, you are not likely to have these properties or proper welding characteristics, right? So when you do the welding, it will not give you the optimum properties, and that may lead to many kinds of defects, like there may be lack of fusion or improper feet up or improper edge preparation, and then you can have this cracking. And yeah, so what are the welding defects I talked about? If I try to note it down, so you have this surface crack, then you have this distortion, then incorrect weld profile, then porosity, then excessive spatter, then you can have this oxidation also, lack of fusion and penetration, then you have blowholes, then you have this shrinkage cavity, then you have this inclusions, solid inclusions, right? So coming to the cracks, we have studied lot about cracks, right? So if we talk about these cracks, we have already studied that there are many reasons, and this is because of high contraction stress. So in terms of cracks, the primary reason is, so I'm covering all the things related to this question. So we'll have this high contraction stresses, right? So when these stresses uh, result into, and its value is more than the strength of the metal at that particular high temperature, in that case the crack result into, and then it may be because of some poor feet up and also some incorrect welding procedures also. So yeah, this way you have this emanation of the surface cracks, and uh, we have already seen that there are longitudinal cracks, transverse cracks, crater cracks. So different types of cracks which are available. And if we talk about different processes, in many cases you can have this different penetrating process, like you have this CO2 welding, then submerged arc welding. So this combined with narrow weld gaps, if they are combining with narrow so these things combined with narrow weld gaps. So as I was saying, that if you're having this narrow weld gap and high heat input, right? They cause these hot cracks, and normally at the root, and hot crack will be form at root level, right? Now, even in terms of welding speed, also high welding speed can cause cracking, especially in aluminum weldments, right? And these are the different reasons for cracks. And yeah, in terms of different cracks, you have this. We have already talked about this longitudinal and transverse and crater cracks. Uh, what should I mention? Hmm. Also because when just but also because so if your material is having some high coefficient of thermal expansion, high, so in that case, like austenitic stainless steel, so their crater cracks are very much likely to happen, right? Now, coming to the question, which of them is not among the possible reasons for crack generation? Can you give me the correct option? So you have this
High
high
contraction.
contraction. This is true. Uh, this results in this. This is a reason for crack generation. This is also true. Poor edge quality. This is also true as I was mentioning. So this is not really the reason of for crack generation during welding, right? So here option three is correct. Anyhow, yeah. Now, coming to this incorrect weld profile. So normally, what you see is that in case of fillet weld, in case of fillet weld, uh, there are different kinds of weld profiles actually uh, in terms of fillet weld. Like there is something called insufficient throat. So it will be looking like I'll not discuss all the things here. However, I will try to draw some of those incorrect weld profiles. How does they look like? So this is something called insufficient throat. The dotted one should be the ideal one, and the solid one is the actual one. Okay. Then you can have this uh, like some excessive convexity in your weld profile, right? Then you can have some overlap also. How 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 do they look like? So you can have some overlap like this, right? So those things come under this those incomplete fusion, then undercut. So those things come under incorrect incorrect weld bead shape, right? Mm, mm, mm. Now, if you look at a proper butt weld, so on both these sides uh, you'll have this convexity, and yeah, right. So apart from these things, you have this surface porosities, right? As I mentioned already. So surface porosity basically occur when the welder is basically using uh, some unshielded electrode, right? So many a times he is using this undried and covered electrodes, or uh, electrodes with some shelf life which has expired, right? So in those cases we'll have this presence of surface porosities, because they contain the moisture, as simple as that, and that basically leads to the presence of these surface porosities, and that need to be avoided, right? Apart from that, you can have many times you have come across the surface oxidation also. So when you are doing this welding of metals, which are very easily oxidizable, like for example of aluminium, the sodium or titanium or magnesium, surface oxidation will take place in those cases, and typically it will happen if you're not providing adequate shielding environment near the surface, right? So in those cases surface oxidation takes place, and that will be certainly uh, if so as I was saying, that will be certain if you are not providing typical shielding what it requires, right? And yeah, so for this question number 3, the incomplete fusion during welding can be suppressed by the use of which one?
Right.
Incomplete fusion is basically happens due to low heat input, really. So your high welding speed also will result in low temperature, right? So ideally, if you say to avoid this incomplete fusion, you have to have require some high heat input, right? So either by increasing the power, so power in terms of you can increase the current setting, or you can increase the voltage setting, or you can reduce the welding speed, right? So you can increase the VI setting reduce the welding speed. Now, many times we also see that you have this excessive spatter for this question. So, uh, you might have the idea that this kind of defect is caused by this arc blow, which is because of wrong selection of electrodes. So, mainly excessive spatter is due to arc blow, that is due to wrong selection of electrodes, or the quality of electrode is bad. So, bad quality of electrodes, or you are using some heavy current. That can be also a reason, right, for excessive spattering. So this excessive spatter occurs because of poor technique of the welder also. So you can have the prevention of the spatter by suitable coating to the metal adjacent to the weld, right? So that way you can have this avoidance of this excessive spattering thing. And apart from that, you have other surface defects also, uh, like in there are arc strikes or so. So when the welder will hold that uh, inadvertently or without knowingly, when it strikes the electrode against the work, so in that case you have the arc strike is taking place, right? So you'll have this unwanted arc, so that can spoil your finished work part. So so these kind of surface defects can occur because of this arc blow thing. Huh. Now uh, what else can we mention? uh, if you come to subsurface cracks, which is also known as some internal cracks. Internal cracks or subsurface cracks, those are basically the example of the cracks which are not seen from outside. So those are not visual from outside, right? Hidden in nature, as I was saying. So they are cracks under the region, and you have also many times you have some small cracks like fissures. So fissures, those are small cracks which are hidden in nature. They are very much dangerous actually, and they are considered to be dangerous because they will be creating a large reduction in the strength per se. So these cracks are more important because they will create certain failure of the material, and especially under the impact load, or kind of low temperature service conditions. So yeah, those things are there. Among them, under subsurface defects, you have this lack of fusion also. These things. This is one of the subsurface. defect. Okay. So basically, it goes like this: you will have this lack of fusion taking place in the region, and that is also called an incomplete fusion. So mostly in case of multipass welding, you come across these cases, and in the case, like the main reason is because of the insufficient welding current, as I was saying here. So many a times you have this, you have the opposite of the electrodes from the axis, or you have the high welding speeds. So high welding speed; those are also the reason of this lack of fusion. So yeah, so just like the undercut, this also reduces the strength, and that will be creating the failure of the component, right? And then you have this porosity or blowholes or porosity. Why they form? They form uh, because of presence of this rust or dirt or something like that, and if you're not able to clean them on the edge of the parent metal or on electrode, so these are the main reason for this blowhole formation or the subsurface porosities, right? Okay, let me choose. Okay, now we have reached into the content of this design for this static loading. Till now we have discussed lot of things in terms of defects, in terms of source of defects, what are the categories of defects, and then now we will spend our time on design for static loading. Okay, initially let us discuss initially initially let us discuss the design for static loading, and then we'll come back to the question. The questions are very straightforward, so there is nothing to worry in terms of answering the questions. uh, yeah, so for a welding metallurgist, if you see, they need to know some certain aspects, right? So like design aspects are there, one of them. So that have that need to be taken into consideration, and that should be given due importance while we go for the welding, right? So first is the design for the static loading. And so in most cases, either you have the static loading or welding may be subjected to some dynamic loading, right? So if you talk about the static loading, uh, mainly we talk about the strength of the material. So the ultimate tensile strength is basically taken as the strength, correct? So that is your UTS. That talks about your welding strength, right? Now it basically talks about whatever material you are taking into consideration, that how long it can sustain, and then what is happening that in most of the cases we will have the occurrence or presence of stress concentration, right? So when you are having the stress concentration in the weld, uh, as the load is getting increased, and then the yield point may be reached soon at the point of stress concentration. So what will happen that what will happen that uh, whenever the yield point is getting reached and some kind of small yielding will happen there, and after slight yielding this maximum stresses will be transferred to the another point of the world, right? And it may be because when you are having somewhat straining, right? And the other point where the other stress concentration is achieved, and there the stress value will be more than the limit. This is how it is happening, right? Huh. So this is how it is happening, and this will be continuing until the stress distribution over the whole load carrying section is uniform, right? So this will be continuing until the stress distribution over the whole load carrying section is uniform, right? Now, yeah. Now this is the balancing of the stress concentration that can take place under some static loading case. So we'll basically take those things into consideration which are required for the designing of the weld, and when the weld is subjected to some static type of loading, as I am mentioning again and again. So in that case, if we talk about this weld design, we normally go for we normally go for the strength of the weld and the rigidity of the weld also, right? So if we talk about the weld design, uh, there are two terms. One is weld strength, sorry, and another is weld rigidity, the stiffness basically, right? So you require in any weld the strength as well as the rigidity, and what we feel that you must have the welds in such a way that it should not fail. Ideally, it should not fail, right? The weld should not fail. So it should not break or yield when subjected to some reasonable overloading, if there is any reasonable overloading is happening, right? So basically, you normally design it. You normally design it for the calculated loading, and for that you may have some design formula for strength and uh, those yeah, deflection also can come into picture. So when you design using the deflection, in many cases, like if you are thinking of the deflection also should not be more than some certain values, right? So uh, so normally happens like if you take any member, but you have to have also take into consideration its own weight of the specimen also. So if you look at the material, you will have to have or you have to consider the material properties, right? You have to consider the material properties uh, like what is E. You have this elastic modulus, then you have I. What is I? This is moment of inertia, and Z, right? Right now. So if you are going for this design formula, so you'll have this you have to understand these terms, like you have stress, strain, and this modulus of rigidity and this section modulus. So this is called section modulus. Forgot to mention. So sorry. So those things will come up, right? And these terms are basically used and the load. So your deflection will be basically calculated in terms of this formula. You have also come across from your strength of material course also. So whenever the load is getting applied, that will be creating the stress on the member, right? And once you have that, so you'll that will be resulting into strain. So you are having the strain, so load will be creating the strain, and the strain is measured in many terms, right? And you may have the strain as elongation, or you may have the contraction, or you can have this deflection, or you can have this angular twist also. So different way you will have the strain which is measured, and every member will be designed according to what type of load, what is allowable strain which is there in particular material, right? So if you're applying this force, in that case you will have the deflection in terms of WL cube by 3 So as we see that here W is the load which will be bringing into the deflection delta. L is your, what is L? L is length of the cantilever beam, right? You're getting deflection like this. This is my delta. This is my W. This is my L, and we have this E and I, right? So among the different materials, if you talk about the values of E and I, that should be large to have minimum deflection, right? E and I should be large to have minimum deflection, right? So then if you talk about this loading condition, there are different types of loads of also which are applied. You can have this tension, or else you can have this compression, you can have this bending, shear, torsion. Different kinds of loads also can be applied in your welding structure. So depending on your load, how much movement will be there, and that we already discussed now. uh, that is depending upon your modulus elasticity of the material and those things. So basically in terms of designing, we'll have this failing stress or factor of safety, right? You'll have this failing stress or factor of safety. So this way you have the definition of allowable stress or working stress, uh, which is uh, what you set for that design of the weld specimen for some satisfactory long run, right? Okay, okay. So coming to the question, designing for the weld for static point loading on the cantilever beam based on the deflection criteria. Yes, this is proportional to applied load. Yes, this is proportional to L cube. Is this proportional to elastic modulus?
No.
No, na. This is inversely proportional actually. So here option 1 and 2 were correct. Okay, okay, okay. So to discuss about these properties, I know that you have already know the relations between E, G, mu, and K. So you know that u equal to 3k into 1 minus 2 mu equal to 2g into 1 plus mu. I'm not getting into derivations. There are basically you can derive it also. That is not very much complicated. Anyhow, I'm not going into that thing. So what I see many a times that we require some high amount of ductility in your structural member, right? So because having that property, basically it will be taking up some to accommodate uh, some permissible amount of strain, and also it will be redistributing the stresses without some permanent or premature fracture. So that way these properties are desired basically. Now now if we talk about this stress strain diagram, mm, yes, of course you have come across this stress strain diagram like this. Here you have point of yielding. uh, Sorry, I'm little bit moving fast. So you have, this is your stress strain diagram, right? So this is your point of yielding and this is your UTS value, and this is your point of fracture, right? And the area under the curve, what does it call? It's called toughness. This is your strain value. Then you have some concept of this group stress, uh, right? And then you have this is your plastic region. So those things you have already come across in your maybe strength of material course. Mm. Now, typically, if you see this stress strain diagram of some steel, so the stress strain, so initially you will see this linear portion, right? Initially, you will see this linear portion, which is there up to this point, and then it becomes non-linear. So the modulus of elasticity of ductile material, uh, how will you define that? This is the slope basically, है ना? This is in the elastic region, right? So, so this is the stress upon strain, that slope that will be known as the rigidity value or modulus of elasticity in normal tension or compression, whatever is there. Then you have this rigidity or stiffness. So that is the amount of stress of the material that can withstand. So that is the rigidity, the strength of the material that can be withstood, right? And then you have this Poisson's ratio, right? Call it Poisson. Anyhow, Poisson's ratio. So what is it? What is Poisson's ratio? Can you tell me?
lateral strain by longitudinal strain.
Right, ratio of lateral to longitudinal strain. So which is happening because when you are straining the material, in that case you will have this change in length as well as change in, if it is cylindrical it can have change in dia also, right? So you'll have this strain in lateral direction as well in the longitudinal direction. So yeah, yeah. So what negative sign of Poisson's ratio tell you? So it tells that basically lateral strain is negative. No. So it tells you that lateral strain is negative to the longitudinal strain because ultimately, huh. So generally, Poisson's ratio basically vary from this 0.25 to 0.35 value. Uh, it can go up to 0.45 for rubber material also. Okay, okay. So coming to here, oh, I already mentioned here E equal to G into 1 plus mu. And coming to another term which is important in these cases, moment of inertia, right? So mainly if you see, this is called second moment of inertia. This is called second moment of inertia. Uh, and yeah, I think I should not uh, spend much time on this thing. So for a rectangular section, if this is your H and this is your B, the width, what is I? H cube by 12, right? Then you have this spherical pi to 2 by 4 by 64 like that. So there are a lot of for different shapes of different shapes or geometry. You can calculate your second moment of inertia, right? So this is basically very useful property of the material in solving this design problems. Yeah. Hmm. How? I hope you are familiar with polar moment of inertia also. So polar moment of inertia usually abbreviated in terms of J, which is basically the sum of any two moment of inertia about axis at right angles to each other, right? So you'll have this polar moment of inertia which is taken about an axis which is perpendicular to the plane of the other two axes. So J is basically will be Ix plus Iy, right? So that way you find this polar moment of inertia. And what else? What else? There is something also, something called torsional resistance also. Uh, hmm, ठीक है. These things anyhow you have gone through your strength of materials. I'm not spending much time on it. Then coming to the fatigue thing, that's the final content of this welding metallurgy session, right? So fatigue loading in welding. Again, we'll initially spend some time on understanding what is happening in terms of fatigue loading, and then we'll come back to the questions, right? So, in terms of characteristics of this fatigue failure, what do you have? So, if you talk about these characteristics of fatigue failure, that normally occur in three stages, right? So, First of all, it will have the initiation of the crack. So first of all, it will have the initiation of cracks, and most preferentially they will be at the surface, and you might have the idea that when you have these cracks, you may either over the surface or below the surface, whatever is there. So they are dangerous, right? And can be easily formed. So when these micro cracks are formed at the surface, so those are subjected to the condition when the stresses are highest at the surfaces, right? And if you have the surfaces where the chances of these micro cracks are maximum, then failure will happen, right? So this initiation of the cracks is thought to be because of stress cycling. Because of stress cycling. So basically in stress cycling, what is happening is it will be resulting into some uh, alternating displacement of the metal along the slip planes. Alternating displacement of metal atoms along the slip lanes, right? So what will happen in that when you have this stress cycling formation, because of that there will be this initial crack, and that will be propagating along the slip plane. And we have seen that normally sleep planes are 45 degree to surface. We have already discussed that also, like this, right? No. So accordingly, if the load on this member is continuing to the same, and so in that case, the crack dimension also will be increased, and that will be increasing your stress. And because as with the increase in the cross section of the dimension of the crack, uh, your effective cross sectional area will be going to decrease. And you know that uh, when your effective cross sectional area will be decreasing, in that case you will have the increase of the true stress value, right? True stress value will be increasing because instantaneous area is getting decreased, right? Now now if you look at the fracture appearance, what will be happening that because it takes time, so with time basically fracture will come out, right? So as the crack is growing, so in between, because of those cyclic stresses and all that, the parts are rubbing against each other, and that will be producing first of all some smooth surface where the failure has been take place. And also you'll have some brittle type or cleavage type of fracture that will be appearing, right? So what we will see is transgranular in nature. What we mainly see is transgranular fracture, and basically we will have two distinct reasons actually. So if you look at the fracture surface, uh, you if you look at the fracture surface, you have two distinct regions of fracture which is present in case of attic fracture. So one is this smooth polished area of original crack, smooth polished area of original crack. And what else? So basically from here the crack has originated, right? uh, that has been subjected to maximum rubbing of the surface. And yeah, and then another is granular area with fibrous appearance of final fracture. Okay. I will be back into for these questions. Before that, let me finish the explanation part. So yeah, those two are the distinct regions, but you can find out in this appearance of crack formation. And then if you try to visualize how this fatigue fracture looks like, uh, you'll have this fracture surface, right? Now now type of fatigue fracture. For type of fatigue fracture, uh, as we have discussed, you have this cyclic loading, and normally you have the failing of the components in terms of number of cycles it has sustained, right? So your material is basically uh, subjected to some load which is fluctuating in nature, and that will be sustaining for number of cycles, and then only that way you will try to have the estimation of this fatigue life of the components, right? So yeah, so this is in terms of Ascent curve. You already know that thing, that through Ascent curve we talk about this fatigue life of the component. And uh, yeah, so here for Ascent curve is AS is your nominal max stress to which the material is subjected to, and N is basically your number of cycles. No? So, huh, huh. And what we mainly see that this will go on asymptotically, right? That means that when the stress level to which the material is subjected to is very small and below certain limit, then in that case you can see that it is going towards infinity, right? And if we go for very large number of cycles, and that the way you quantify or you interpret the fatigue life of the components, right? So yeah, and then you have these factors affecting fatigue life. Factors affecting fatigue life. You have this material properties. Then you can have this joint configuration. What else? Then you can have this stress ratio, the stress triaxiality. Then you have this residual stresses, right? Those things are there. Some loading conditions also, right? So when we talk about these material properties, what happens is that uh, at one side you have this UTS, and on the other side you'll have this endurance limit. So that's how you define it, right? So the graph will say that normally for many materials. Now the thing is that when we talk about the material, so for a typical material, if you talk about the property for any particular material, the fatigue behavior will be depending upon this uh, surface properties or surface characteristics, in fact, right? So yeah, so what is seen that if you talk about this UTS and fatigue if this endurance limit now, uh, so when you have this polished surface, when you'll have some type of polished surface, so that time your endurance limit value will have the approximately some it will be about half of the UTS value, right? And when you have this notched specimen or some corroded specimen, notched or corroded specimen, in those cases your fatigue property of the material will be getting changed, and this is shown for steel. Normally it is mostly seen that material properties affects the fatigue behavior of the material, right? Okay, coming to the question, which of the following statements are correctly explain the fatigue loading? Here it says the change of observed in material under the influence of stress generated during cyclic loading, and the material usually fails at higher value of stress uh, than that in case of static loading. This is not true. This is only the true statement, right? So here option 1 is correct. This one. Agreed, no?
Yes, sir.
Then you have this life of a welding joint subjected to fatigue loading is represented by Asen plot. Option 3 is correct. In compressive loading, the component is designed against tensile loading or buckling or torsion, or both tensile and torsion. Which one it should be?
Buckling.
Right. I have restriction in time for this design against this fatigue loading anyhow. Just a minute, huh? Huh. And then in your final question, what it will be? Fatigue life of the welder joint is
Directly proportional number of cycles.
is it direct?
Sorry, inversely proportional.
Right. It's inversely proportional to the number of cycles. Oh, that's it really. That's it really. Oh, oh, हाँ, ठीक है. So in terms of this bending theory, what can you tell me? What is the equation? So you have this m by I, which is this m is your external bending moment at the section, and that is basically equal to E by R, which is equal to sigma x by y, right? What is sigma x? This is your bending stress, right? This is your bending stress at some perpendicular distance y from the neutral plane, at some, you remember that, right? Perpendicular distance y from neutral plane. And what is r? R is your radius of curvature, and you know what E is. That is your Young's modulus, right? So basically, what happens in case of compressive loading, like if you come to compressive loading, the members will be subjected to some kind of crushing if your compressive strength exceeded the stress which is generated more than the compressive strength of the material, right? So but that is very rare, but that is very rare that case comes under the compression case. So mainly what we need to design is as you say that mainly we need to design it for buckling. And yeah, because depending upon the length of the member, because upon depending upon length of the member, you can have uh, this slenderness effect, है ना? So you can have this slenderness effect that can come into picture. And yeah, So if you have these columns, then you can measure this slender ratio, right? Slender ratio you can measure for columns, columnar structure. I'm going into strength of materials anyhow. So how your slenderness you can measure. So that is basically measured at the ratio of this unsupported length L to the radius of gyration. This is unsupported length. This is radius gyration. So when your slenderness ratio will be higher, it will be more chances to buckle, right? Slenderness ratio is higher, buckling possibility will also increase, right? That's it really. Any question? Okay, so we'll finish up here. This was our last session. Okay, chalo. Okay, bye bye. Have a good day.
Thank you.